Chapter 1 with some more exponent stuff, particularly zero and negative exponents. Again, historically I found that kids have more trouble with this than they seem to realize or are willing to let on, so please don't hesitate to ask questions on this if you're struggling. In lesson 131, you use the meaning of an exponent to rewrite expressions such as y to the 4 times y squared, which would be y to the 6th, or x squared times y to the 3rd, that would be x to the 6th, y to the 3rd. Today you'll use patterns you discover to interpret expressions with exponents that are negative or zero. So we're going to come up with some rules, and then we're going to look at zero and negative exponents and see why they work the way they were. Again, on this one, 7x's times 4x's is 11x's. On this one, I have 3 sets of 3, so I have 9. On this one, I have 14 on top and 2 on bottom. It is not 7. It is 12. Again, 2 cross out from 14 and leaves me 12. Here, I have 4 sets of 2, which would be 8, and I have 4 sets of 2, which would be 8. On this one, the 5 on top fight the 2 on bottom, and it leaves me 3 on top. And the 11 on top fight the 3 on bottom, and it leaves me 8 on top. It looks terrible. That's a 3. On this one, again, don't forget different rules for the bases. 2 over 8 is a fraction that we just simplify to 1 over 4. And now I have 12x's on top and 2x's on bottom. They cancel each other out, and I'm going to have x to the 10th. By the way, you don't have to have this 1 here. It's irrelevant. If you want to put 1x to the 10th over 4 or x to the 10th over 4 and write it like this, they have the same value. Okay, so I hate this part. I'm going to ignore this here. But it says, using the table below, summarize the patterns you found in problem 173. For each expression in the table below, rewrite the given expression in a simpler form, and then write an expression that represents its generalization. Then in your own words, explain why the pattern works. So if I have 25x's times 40x's, I have 65x's altogether. So if I'm multiplying x to the m, what that actually means is I'm going to take x to the m plus n. Why is this true? I don't know, because 25x's times 40x's is 65x's, so I added them. I don't know what you would write here. On this one, if I have x to the 36 divided by the 13th, again, 13 are going to cross out from 36, and it's going to leave me x to the 23rd. So really what the rule I'm saying is I'll take x to the m minus n. And again, why is this true? I don't know, because I subtracted. I just don't know what to say here. Here, I have 12 sets of 5. Well, if I have 12 sets of 5, it's like 60. So what is my rule here? Well, I guess I'm going to multiply the m times the n. So we have these shortcuts that we can use. We can write it out and put 65x's, or we can just use the shortcut and realize I'm going to add there. And we can cross these out, write 36 and 13 and cross them out and count what's left over, or we can use a shortcut and realize that we're just subtracting. Here we can write 12 sets of 5, which would be 60, or we can just realize that we're going to multiply that. So these are the generalizations of the shortcuts that we're going to use. Now it says rewrite each of the expressions below twice, once using repeated multiplication and once use the giant 1 to simplify. So how about this? We know that this will equal 4 minus 5, x to the negative 1 is equal to 1, 2, 3, 4 over 1, 2, 3, 4, 5. Now think about this. This is going to cancel out, and it's going to leave me 1 over x. So interesting. X to the negative 1 equals 1 over x to the first power. Kind of interesting. What about this one? 2 minus 4. 2 minus 4 is negative 2. Or we have x over x times x, 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 x. These cancel out, and it leaves me 1 over x squared. So again, kind of interesting. You can see what happens to a negative exponent. How about this one? Hopefully we're already beginning to see the pattern here. 7 minus 10 is negative 3, right? That looks terrible. I'll just rewrite the whole thing. Or what we're going to have is 1, 2, 3, 4, 5, 6, 7 x's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 x's. Cancels out. This looks amazing, doesn't it? And I have 1 over x to the third. So we're beginning to see our first pattern here, that if you have a negative exponent, it moves to the bottom and turns positive. If you have a negative exponent, it moves to the bottom and turns positive. I'll say that one more time. If you have a negative exponent, it moves to the bottom and turns positive. So here's the second thing. Investigate x to the m divided by x to the m. Well, that would give us m minus m, which would equal x to the 0. And think about it. Also, x to the m over x to the m cancels out and just equals 1. So there's another pattern that we have. Anything to the 0 power equals 1. So a negative exponent moves across a fraction and turns positive, whereas anything to the 0 power is going to equal 1, which is interesting. And I'm going to take a break right here, and I don't usually teach it this way, but I think the book does a good job of this, but I want to go through this the way I normally go through this. So two different ways. Hopefully they'll both make sense, and if not both, hopefully at least one of them will make sense. What if I had something that looked like this? What if I had 3 to the first power? I hope we all agree that the answer would be 3. And if I had 3 to the second power, you would get 9. And if I had 3 to the third power, you would get 3, 9, 27. If we had 3 to the fourth power, 3, 9, 27, 81. So you can see in this direction I'm multiplying by 3, but what's happening in this direction? It looks like I'm dividing by 3, right? So if I go in this direction, 4, 3, 2, 1, 0, well, what is 3 divided by 3? It's 1. And there we see that same rule again. Anything to the 0 power is equal to 1. And what if I went again? 3 to the negative 1 power, right? Well, what is 1 divided by 3? It's 1/3. And what if I went again? If we get 3 to the negative 2. Well, think about it. What is 1/3 divided by 3? We never divide fractions. We always multiply by reciprocals. So it would be 1/9. And what is 1/9? Isn't it 1 times 3 to the second? So you can see that negative exponent moves across the fraction and turns positive. I'll do one more. What if I went to 3 to the negative third? Well, it would be 1 over 3 squared, or 1 over 9 divided by 3. But again, we don't divide fractions. We multiply by reciprocals. So it would be 1 over 27, which is 1 to the third power, 3, 9, 27, right? So you can see again another example of how those negative exponents move to the bottom and turn positive, or how a 0 exponent should equal 1. Whether you like the way the book just did it or the way I did it, it doesn't matter. The rules are the same. We need to make sense that we understand that. So anytime we have a negative fraction, it moves across a fraction and turns positive, to the point where this is also important. I'll kind of get ahead of this a little bit because this is going to come up at some point. What do you do if you have like a negative exponent on bottom? Well, it's going to pop to the top and turn positive. So if it's a negative on top, it goes to the bottom and turns positive. But if it's negative on bottom, it moves to the top and turns positive. So again, if you have 1 over, I don't know. Well, let's say you had x over x to the negative third. Well, that x would just stay right where it's at. These x's would move to the top and turn positive, and you would just have x to the fourth. So I hope you kind of see what's going on. Tricky stuff for some people for sure, but there's a lot going on with exponents that we need to understand. So let's go ahead and get a clean slate and keep going with this. So we've done that, we've done these. So now we're down here. It says expand as needed in order to use a giant 1 to rewrite each of the expressions without any negative. By the way, you never have a negative exponent when it is simplified. So here, my advice to you would be write what stays, right? Like 18x squared is going to stay on top because those are all positive. Don't forget that 18 has an exponent of 1. That 30 is going to stay because it has an exponent of 1. That x to the fifth is going to stay because the exponent of 5. That y to the negative 1 is going to jump to the top and turn positive. Now I will attack this problem. Now I will kind of look at this problem again through fresh eyes now that I've gotten rid of the negative exponents, and I can simplify. What is 18 divided by 30? Well, 6 goes into 18 3 times, and 6 goes into 30 5 times. So I've dealt with the bases. Now I'll deal with the x's. 2 x's on top, 5 on bottom. I cancel them out. I have 3 x's on bottom. And this y, nothing happens to it. It just stays by itself. So that will be the simplification of a. if I look at b, again, don't get confused on negative bases versus negative exponents. These have positive exponents, okay? So I'll go ahead and just set these things up. Negative 5 to the first power on top. X to the negative second, well, that's going to move to the bottom and turn positive. That's x squared. Y to the first power, it's going to stay up top and be positive. Negative 2 to the first power is going to stay up top. I'll put this in parentheses and be positive. X to the third is going to stay up top and be positive. And y to the negative 2 is going to move to the bottom and be positive. I'm going to go ahead and make myself a little bit of room here. So I'm going to keep going. Okay. That bothers me. All right. So I'm going to keep going in this direction. So now on top I have negative 5 times negative 2, which is obviously 10. And then I have x to the third and y. I'm just rewriting. And I have x squared and y squared. Now I can simplify this thing. So I have 10 on top. Here, 3x's on top, 2x's on bottom. They cancel. I have 1x on top. Here, 1y on top, 2y's on bottom. They cancel. I have 1y on bottom. So after all of that, my answer is 10x over y. So it looks kind of crazy. So I'll go ahead and put this 10x over y, but I'm going to need to obviously erase this work to uncover the last problem. So there we go. And again on this one, I'll kind of go up here just so I have some extra room. 15 to the first power stays on top. X squared positive stays on bottom. 1 positive stays on top. Doesn't really matter, right? 15 times 1 is 15, so I'll just leave that. I'll ignore that 1. This 45 is going to stay on bottom, though, because that's 45 to the first power. That x to the negative 3 is going to move up top and turn positive. Now I can kind of rejigger this. I have 15 x to the third over 45 x squared. At this point I can simplify. 15 goes into 15 once. 15 goes into 45 3 times. And then 3 x's on top, 2 on bottom, they cancel out. I'll have 1x. So after all of that, after all of this, this is my answer. So not too bad if you go step by step, but a lot going on for sure on these. All right, let's go ahead and answer this. I'm definitely going to want a calculator to help me a little bit here. So if I go to this one, it says a size 7 shoe is about 1.4 times 10 to the negative 1 meters long. The circumference of the earth is 1.06 times 10 to the 7th around the equator. How many shoes end to end would it take to wrap up the equator? Show expanded and use your giant 1. I don't know if I'm going to do that. So long story short, I'm going to divide 1.06 times 10 to the 7th divided by 1.4 times 10 to the negative 1, because I'm dividing the earth by the shoe. I'm not dividing the shoe by the earth. I hope that makes sense why this went on bottom and that went on top, because this is the earth and this is the shoe. So if I look at this, I get 1.06 times, I guess I will do it, 1, 2, 3, 4, 5, 6, 7 tens, right? This 1.4 is going to stay on bottom, but this 10 to the negative first is going to jump up like this. So now what I'll do is I'll simplify this by dividing. I'll grab my calculator. I'll divide 1.06 by 1.4, and I will get, we'll just call that 0.76 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, and that makes sense because I have these 7 plus this 1. And here's the problem, I'm not in scientific notation. So again, dealt with the bases, dealt with the exponents, now I need to go times 7.6 times 10. And the question is, if I go in this direction, am I adding or subtracting? Of course I'm subtracting, so times 10 to the 7th. So, oh, I didn't put a 10. Bummer. Times 10 to the 7th. I will tell you, a lot of times I get screwed up if I'm going in one direction to the other. It's okay to just sort of say like 0.3 times 10 to the second and just do it as an example and say, well, if I did this, I would go 2 in this direction, right? And then I would need to go 1 back, so this equals 3 times 10 to the first. So you can see I had to subtract one exponent. Well, I did the same thing. I had to subtract one exponent. I just think it gets a little bit tricky. So sometimes off to the side, I like to do something like this to help myself. All right, kind of a long lesson, it feels like. I'm just going to close this real quickly, and then I'm going to open up the B, 1.32b, to see if there's anything else I missed. So we have exponent concentration. There's like a card game that we don't usually play in class, so not worried about that. You should probably fill in your learning log. And then you have some laws of exponents in the math notes, so I would look at those. I think there's more that got cut off here that I would definitely make sure that you're responsible. If you have the note page that come with this chapter, I would definitely make sure you understand these laws of exponents and the shortcuts that go with them.